Okay, so what we've been talking about last week is we're talking about memory management. And, oh, you guys can't see any of this. Well, hold on. Okay, so we were talking about memory management. And we'd mentioned a couple of things that I wanted to go over, quick review. Two different concepts of memory. There is the fast, expensive, non-persistent memory that is on the RAM, okay? That's what we call physical memory. That's the memory that can be directly accessed and read into and out of registers on the processor, okay? Then we had logical memory, okay? That's the slow, less expensive, but persistent memory, okay? That is actually stored on disk, okay? And every process, so each process maintains its own internal idea of what its memory is like. And this memory goes from 0 to m-1, where it takes m memory addresses, okay? And this internal representation, which is consistent internally to the process, each individual process, is called its logical address space. Okay. Now, the logical address space is not accessible, okay, for the processor to do any processing with until this logical address space gets loaded on into actual RAM, okay, which is the physical address space. Right now, we will generally believe, okay, I'm okay believing, although this not necessarily have to be the case, but we're okay believing the general case is that the physical address space, which goes from 0 to n-1, where n is the total number of discrete addresses in RAM, we're okay believing that n is going to be not only greater than, but probably significantly greater than m, okay, for any value of m for any of the processes. Now, that's not strictly true necessarily. It's not necessarily true, but it's usually going to be true, and we're okay with that generalization. So what that means is that we're going to be loading multiple of these logical address spaces into our physical address space. And so a lot of what we talked about last time was how do we map the logical address spaces, which always start at 0 and go to m-1, where m is some value that is local to the process. It's process specific. How do we load those into physical address space where they're not all going to start at 0 in actuality, okay? And they're going to be laid into the physical address space anywhere between 0 and n-1, okay? So all the address references that are inside this logical address space, which reference the logical address space, are going to have to be updated in some fashion to now represent the truth on the ground, the physical address space about where those instructions and data are actually stored when they get loaded into physical memory, okay? And that was the notion of address translation, okay? And hopefully you remember these details because this is all review. This is what we talked about last week, okay? And I'm not going to go into any more detail today about what we've talked about previously, but we mentioned some methods for doing address translation and for some considerations that go into that, Okay, so I kind of expect that you've worked through that, in your studies. Okay, I can remember some of that. One thing to keep in mind, and that we're going to have to just wrestle with, is that we are dealing with insufficient physical memory. That is to say, we do not have enough physical memory to keep track of all of the logical address spaces for all of the processes that are running simultaneously on the system. Okay? So we are going to eventually run out as processes come in, as they get started up, we're going to run out of room in physical memory, which means that when processes terminate or when they go to the blocked state, then their address spaces need to be unloaded from memory, okay, written back out to disk, okay, stored again as a logical address space internal to the process, so that some other process's memory can be loaded in its place. Okay, this is the notion of swapping. Okay, and we talked about that. And we talked about some of the complications that come with that. One of the complications that comes with that is this notion of external fragmentation. Okay, we mentioned that logical address spaces get loaded as chunks, which are called load modules. So external is called external because it's external to the load modules themselves. So like between load modules, right? It's external to what is inside of each process's address space. And external fragmentation is what happens when we load a bunch of things in memory and we ultimately remove some things from memory. Okay, we loaded them all. This was all completely loaded up with load modules, and then these modules finished, okay, leaving behind available space. Okay, so there's available space here, there's some available space here, some available space here, and some available space here inside of RAM. Okay, and these available spaces are, again, they're called holes. And we need to fill these holes, and of course RAM goes on. We need to fill these holes in some fashion. And the way we want to fill them, right, is to prevent as much fragmentation of the memory as possible. Can you name some or all of the 4 methods for doing that? First fit, best fit, worst fit, next fit. Exactly correct. Okay? Those are all 4 versions of methods for how to do this. And what did we say at the end of class last week about those? We don't know in general that we have any argument to suggest that one of those is better than any of the others. Okay? It seems like with this external fragmentation is just something that's going to happen. Okay? So you're like, well, great, we'll just have more memory. We'll increase the size of RAM. And yeah, that does work, of course, for a while. But if you increase the size of RAM, let's say you do something like fundamentally put more RAM for less money on a chip, okay? And you give all your computers more RAM, and it's less expensive RAM because of technological developments, then what's going to happen is your programs are just going to get more advanced and require more RAM, and your computers are going to run more programs, okay? So it's not like we can increase the efficiency of RAM and catch up with the possible increase in demand across hundreds or thousands of programs, okay? So that hopefully motivates us to think about a different approach, right? Is there a better way to organize how we are going to load logical address space data into the physical address space, okay? And this all comes down to something that's called paging, okay? Paging. What's a page? Okay, so a page. A page is a fixed size chunk of logical address space. Okay. So what we're effectively doing is we're dividing up all of our many logical address spaces into chunks of pages, okay? And we're dividing them up into a fixed size chunk, right? And then we're going to move around those fixed size chunks. So this is the smallest amount of memory to be loaded or unloaded from RAM. Now, that's not because of a hardware limitation. That's because that's how we're defining it when we do paging. Okay, we're gonna load pages, whole pages at a time, and when we need space, we're gonna unload a whole page and put another whole page of the same size, maybe from the same process, maybe from a different process, in its place. Okay, does that make sense? The fixed size that we have is called the, oh, you'll love it, page size. I know, right? Never would have seen that coming. Okay. The page size is not only the size of the page, okay? And the page is like a carved up logical chunk, a chunk of a logical address page, but the page size is also the size of all the page frames, okay? So the metaphor is like framing a picture, framing a photograph. If your photograph is a 5x6 photograph, you need a 5x6 frame to fit that photograph into, okay? And what a frame is a chunk, a fixed size chunk of RAM or physical memory. Okay, so we have divided up physical memory into some number of fixed sized page frames. Each one of them is the exact right size to put a page into for processing. Okay, if we run out of page frames, we swap entire page frames out, not load modules. Okay? What does this do for us? If all of the frames are the same size and they're competing, and they're competing for RAM, for space and RAM, and they are all the same size, right? So this one can go here, this one can go here, this one can go here. There's no leftover space in between these page frames, okay? So this eliminates external fragmentation. Okay, does that make sense? Any questions so far? Okay, so how do we do this? How do I divide things up into pages and page frames? Let's look at, for this lecture, I've stolen several diagrams directly from Zybooks because I think they do a good job. Ignore the colors for right now, right? But what this is RAM. Okay, it's a tiny chunk of RAM that can be addressed with 1, 2, 3, 4, 5 bits. okay? So that's what, 2, 4, or 1, no, 2, 4, 8, 16, that's 32 locations, okay? And by the way, these are called words, right? We talked about that. I didn't mention that in my brief review, but each of those address spaces is one word long, okay? Some number of bits long. These are not bits that store data. These are the bits that are being used to address each of these words in memory, okay? So those are addresses. This memory has 32 words in it, okay? I don't know how long they are. It could be any length. It doesn't matter to me. Okay? All I know is that there are 32 uniquely addressed spaces in this memory. And the same thing is true for this memory, okay? Because it's the same memory. 32 bits is the address space. Or rather, 32 bits is the number of addresses. Okay? It only takes me 5 bits to address 32 addresses. Does that making sense? So how do we divide these up into pages? How do I divide this logical address space into pages? Well, the size of the page. So this page is the same as this page is the same as all the other pages on this left-hand version of memory right here. The size of the page is directly proportional. It's decided by how many bits of the address that we use to represent the page, okay? So if we use going right to left, if we use the rightmost 3 bits, okay, then we're going to have pages that are 1, 2, 3, 4, 5, 6, 7, 8 words long. Okay, and then the next page is also going to be, because we use 3 bits, 1, 2, 3, 4, 5, 6, 7, 8 words long. Okay, 2 to the 3, in other words, right? Because we use 3 bits. So the 3 bits that we used, however many bits we used, to represent the individual words in each page determine how big the pages are. And the other remaining, in this case, 2 bits that aren't being used to address individual words inside of a page address or create the page number, right? So all these addresses inside the page are for page 0. All these are for page 1, okay? The next one would be page 10, which is 2. And the next one after that, 11, which is 3. Okay? So how many pages did we divide this up into? Well, we used 2 bits to represent page numbers. Okay? How many numbers can I get out of 2 bits? 0, 0, 0, 1, 1, 0, and 1, 1. So that's 4 total pages. 4 pages, and each page is 8 words long. So that's a total of all 32 words out of memory. Okay, does that make sense? Take the same memory, and we can get more pages, each of which is a smaller size, by only using the rightmost 2 bits to address all the words in a page, right? So if I only use 2 bits to address all the words in a page, then there must be a limit of 4 words. There must be exactly 4 words per page, right? Then the remaining 3 bits of the address are the page number, okay? And with 3 bits, okay, I can get 8 page numbers, or 8 pages, right? 1, 2, 3, 4, 5, 6, 7, right here. That's a total of 8. Okay? So all I'm doing is I'm taking the address space, okay, the addresses, and by choosing where to divide up that address, Okay, all I'm doing is deciding both how long each page is, what its page size is, in other words, and the page size will then determine how many pages there are, because there can be no more pages than will fit that number of words, a page size number of words, in the total amount of memory that I have. All right? Ask me questions. So what does that have to do with page frames? Well, instead of logical memory, what we're doing, this chunk right here is just the second column from the last diagram we looked at. Okay, it is a logical address space where I have used 2 bits to address the words in every page, which means I am using the remaining 3 bits to be the page number. Okay, which means that I have, since there are only 5 bits, that means that I have 8 pages. Okay, for this process, right? 8 pages for this process, because that's limit. The limit is because there's only 32 words in this process's logical memory, right? That won't be true in general across all processes. But what must be true in general across all processes is that they must all have decided to use the same size pages. Okay? Over here, I've got my physical memory. And you'll notice that it is also divided up into page frames that are the same size as the pages. They also make use of 2-bit values to keep track of the words, the address of each word in each page. So that means that there are, again, 4 words per frame. Word 0, word 1, word 2, word 3. Okay, word 0, word 1, word 2, word 3. Word 0, word 1, word 2, word 3. But the frame numbers keep updating, right? 0, 0, 0, 0 for 0. 0, 0, 0, 1 for frame 1. 0, 0, 1, 0 for frame 2. Okay? And there are, in this case, physical memory for this really weird, really small computer has 64 total addresses, total words. And that means that there are 15 frames available for use, all of size 4. 16 total frames for use, all available of size 4. Well, that's good because these pages, which need to go in those frames, are all also of size 4. Okay? So how do we turn a logical address into a physical address? We take the logical address, in this case, 0, 0, 0, and then some offsets, X and Y. And I turn the lights off because it's very difficult to see that light yellow shadow highlight, okay, when the lights are on. But that's meant to show that this page number maps to this frame number, okay? So somewhere there's got to be a table that maps all the page numbers, okay, for each process to the frame number in physical memory. And what that means is that every process also keeps track of a page table. Okay? And the page table merely has the page number and the frame number listed in it. Okay? So in our example, page number, not that one, page number 000 maps to frame number 1. Okay? And page number 011 for 3 maps to frame number 111 for 15. Okay? Every process needs to have its page table stored. Okay? So when I need to translate an address in the form of a P part and a W part into an address in the form of an F part and a W part, right? I look up the P part in the page table. I identify the F that goes with that, and I put that F over here. And then I just transfer this W over here to give me the offset for that page/page frame, because pages and page frames are the same size. Okay? So this address for each individual word in that page will also be the address for the individual word in the page frame once I have looked up the proper frame in the page table. Okay? All right, questions about that? Nothing? Clear? Good? Okay, clear as mud, right? All right, so downsides to this. All right, sounds great. Sounds like this is what we should do every time. All right, there's a couple of downsides to paging. So problems with paging. It eliminates, the good thing about it is that it eliminates external fragmentation, and we do not have to worry about doing any kind of assessment of best fit, next fit, worst fit, first fit, anything like that. That we relieve the operating system of having to worry about that, because there are a fixed number of page frames, and every time we need a new page frame, we swap one out for the page that we need. Okay? And we empty a page frame and put the new page in it, right? And we have an easy way to translate addresses doing it that way. So it eliminates all the overhead from having to worry about external fragmentation. However, there is this new problem called internal fragmentation. Okay? If I have a load module, okay, that is, say, this big from 0 to m-1, and I have a page frame that is this big, okay? These are supposed to be the same size. You try freehanding it. But those are meant to be the same size. Then I've got a little bit left over right here. It's not like I can just leave that out. That needs its own page frame. Okay? Then what happened? Well, now there's empty space down here, right? Unused parts of the page. Well, that doesn't break anything, okay? Because I can just move, this says this is P1 and this is P2 and this is P3. Well, then I'll just have a table for pages and frames, and I'll keep track of where P1 is and what frame it's in, and where P2 is and what frame it is, and then where P3 is and what frame it is, and we'll just move around this empty garbage, okay? But when you've got pages that have empty garbage, and they don't extend to the end of the frame, right? That's kind of like fragmentation. There are still holes in memory, right? It's a little better than external fragmentation, all right, because we still don't have to worry about it, but we are not making maximized use of our memory when we do that. Okay? Maybe we're okay with that though, okay? Because the overhead for cleaning that stuff up is just maybe not worth it, right? It's easier this way. Okay, so that's problem number one with paging, right? Problem number two with paging is a little more serious, right? Our load modules, say this is a load module. This is the memory for our process, okay? The logical address space. It really is divided up though into instructions, right? Static data, okay? The stack and the heap, okay? Are they all going to be the same size? No. No reason to believe that they'll all be the same size. No reason to believe they'll all be one size in particular. Okay? No reason to believe that between processes, the instructions for one process will take up the same amount of space as the instructions for another process, and same for all those other parts. Okay? The problem of internal fragmentation really gives us fits when we are internally fragmenting, like the stack, for instance. Okay, so this is P1, P2, P3, P4, P5, right? If we're splitting up the instructions, or we're splitting up the static data, or we're splitting up the stack, or we're splitting up the heap, that causes us a lot of overhead and a lot of problems, right? Yeah, because it makes it difficult to access all the data at one time. It makes it difficult to ensure restrictions on the data. It makes it difficult, just in general, to use the data. Right? Sharing and protections of logical components become difficult to ensure, right? As they're being loaded in to separate frames, splitting those components into separate frames, spreading them across RAM. Okay? So, what next? All right, let's try a different thing. Instead of paging, let's try something called segmentation. Segmentation. Where do you hear the word segmentation? Where do you see that word? Okay, I mean, you're not wrong, but that's not what I'm thinking of. In your programming life, as programmers, where do you see the word segmentation? Do what? Still not what I'm thinking of. Still not what I'm thinking of, although it might have to do with functions. So segmentation of fields, bits. Okay. So I asked this question in the other section, and they got it right away. You guys are more inventive, I guess. What? Huh? Start? Stack. Stack segments. Yeah, like all of those are different notions of the word segment. Where this comes up, where it's a headache the most often, is a segmentation fault or a seg fault, right? You've certainly run into seg faults before. You're running a program. I know in Ubuntu, for instance, if you run a program and it has a seg fault, it actually tells you segmentation fault and ends the program, right? Have you seen that that error pop up before? Tell me you have. You guys are just brilliant programmers. Or more likely it gave you a different error, right? That was actually resulting from a segmentation fault. The reason why that happens is because you are trying to access memory that you do not have access to, right? So when you try to access memory that you don't have access to, and that comes up all the time, especially like if you're doing dynamic allocation with arrays or some other data structure, and you try and access an address that's past the end of what you have access to, you'll get a segmentation fault, and that causes the program to terminate. I bring that up because our discussion here is gonna highlight what is actually meant by a segmentation fault. Okay, let's start by saying what a segment is. So what is a segment? It is a variable size chunk of logical address space. Okay? How does that make it different from a page? It's variable sized and pages are fixed size. Okay? We also need a segment table. Okay, so each process is going to have its own segment table that keeps track of, it ties each segment by segment number to a specific location in physical memory. Okay, so in this approach, gone are the notion of fixed size pages and page frames. Instead, we're going to divide up our load modules, our logical address spaces, into variable size chunks. Why did we do that? Because we can make a segment for instructions. Okay, we put all the instructions in a segment. Okay, we can put all the static data into its own segment. We can put all the stacks, all of the stack rather, into its own segment, and the entire heap into its own segment. Okay, so we break the load module into smaller chunks, which makes it easier to load. Okay, but they don't necessarily have to be fixed size chunks, so that we can keep the logical components of the load module together inside the same chunk. Does that make sense? And the addressing for this is not very different from what we had done before with paging. So the logical address is the segment number and the word offset. And the size of the segment, okay, is variable though. Okay, so the size of the word that addresses that segment will be variable. Okay, so when we look up a segment in the segment table, what we find are two pieces of information: the size of that segment and the segment address. That would be the address in physical memory where that segment has been loaded. Okay, if the address, the offset that you are looking for inside that segment is bigger than the size of the segment, that means you are looking past the end of the segment for some address, in which case you get a segmentation fault. An error is thrown. Okay? So if you're looking in the heap for something that you dynamically allocated, okay, and you're looking farther past the end of the heap and you go past the segment that encloses the heap, then you get a segmentation fault as a result of that. The W offset of the address that you're looking for inside that segment is farther away than the size of the segment from the start of the segment. Therefore, it can't be in that segment. Therefore, you have an error. You're looking in the wrong place. Okay? If it's not, if the offset that you're looking for in the segment is not bigger than the size, then we're going to look up the segment address, and that's going to tie us to an address in physical memory, and then the offset will tell us how far down from the start of the segment we want to go to find the place in memory that you are looking for, the place in physical memory that you are looking for. Okay? And so by doing this, by doing SW, looking up S in the segment table, checking that W is not bigger than size, finding SA, and then doing SA plus W, we'll get the location of the SW logical address that you were searching for. Okay? So that's how you translate from a logical address into a physical address under segmentation. Like I said, it's not a whole lot different of an idea than paging. Okay? What's the downside to doing this? Well, we mentioned this already. What's the upside to doing it this way? Why do we want to use segmentation and not paging? And what's that good for?
It allows you to change the size of the segments versus where page framing is a specific size.
And why do I want variable sizes? Why do I want to change the size?
So you use all the space in memory and not go over.
No, not quite. Because I want to keep the logical components of the load module together in their own chunks. Okay? I want to keep the data together. I want to keep the instructions together. I want to keep the heap together. And I want to keep the stack together. Okay? Right? So that's why I'm using segmentation. That's the argument for using segmentation over paging. What's the argument against using segmentation over paging, though? I haven't said it specifically, but there's a reason why it was good to have a fixed page size. Why do we do that? I did say it was only about 15 minutes ago. What are our options? Our options are swapping, okay, swapping in whole load modules versus paging versus segmentation. We said why we wanted segmentation, okay? But why did we want paging in the first place? Paging with its fixed page size. What good was that? What was the benefit over swapping? No external fragmentation, right? No external fragmentation. Does segmentation allow for external fragmentation? Yeah, for the same reason that swapping does. Because the chunks that you are moving into and out of physical memory are variable size, which means that the holes you leave behind are going to have to be big enough, and you're going to have to check to make sure that the hole is big enough before you can load each segment into that hole. And if you do identify a hole that is big enough, is that the hole you should use? Right? Because we want to leave behind large holes when we load things. So now we're back to the original problem of best fit, worst fit, first fit, next fit. Okay? Instead of doing load modules, instead of doing whole address spaces, though, now we're doing segments, which are smaller, right, but still lead to external fragmentation. All right, so paging, we did paging for a reason. It eliminates external fragmentation. However, it does not pay attention to logical components, right? And we did segmentation, which allows us to group logical components into the same chunks, but it does allow, it doesn't prevent external fragmentation. So is there yet another way forward? Can we combine paging with segmentation? Okay. Yes, we can. All right, how do we do that? We take the logical address space, okay, and we convert it into multiple variable size segments. That's what segmentation does. But each segment is then divided into fixed size pages. And the physical memory is divided into fixed size frames, okay? So that allows us to keep the chunks together, right? And allows us to eliminate external fragmentation. Okay, it looks like this when we do the address translation, right? You get your segment, you got your page, and you got your offset. And we have divided the logical address space into those three components, okay? The leftmost bits tell us which segment. The rightmost some number of bits define how big the pages are, okay? And the middle bits between those two give us a page number, okay? So when you have a logical address that is SPW, the first thing I do is I look up S in the segment table, okay? And I got size, just like before. It tells me the size of the segment, and it tells me the page table location. The page table, I hesitate to say address, but let's say index, okay? And so we still do this check. If your page number, your offset, is bigger than the size of this segment, then you have looked past the end of the segment when you did your addressing, and therefore you get a segmentation fault, you get an error, okay, which causes the program to terminate. When does this happen? During runtime. Yeah, okay. All right, so if that's not true, we look up your index on your page table, and we find that, hey, look, this goes to here, let's say 0, right? Or rather, we look up P, which is the index for your page table, and we find there that it has F, which is the first address in physical memory, okay? The place in physical memory where your page has been loaded. And then all you have to do is look up the offset W to go W steps down to find your location, that address translated from logical addresses into physical addresses. Okay? Does that make sense? It's probably not as good as segmentation in the sense that you're no longer guaranteed that all of your logical components are going to be in a single chunk in physical memory. But you're at least guaranteed that the only thing in that chunk in memory is all that data is from the same logical component, right? So like there's going to be all data in this segment, or all stack in this segment, or all address in this segment. It might not be your entire, not address, but operations, instructions. It might not be all your instructions, but you know that it's only instructions in this segment. Okay? And it does prevent, this method does prevent external fragmentation. Again, because we're using fixed size pages that fit inside of fixed size page frames inside physical memory. All right, any questions about this? There is one other problem here. I said this error happens at runtime, and maybe that's a clue to what this problem is. You want to take a stab at it? It's not that they're not the error itself, not the runtime itself, but the error that happens from the page lookup happens at runtime. I don't know, maybe that's enough of a hint. What's the problem with this approach? It's the thing that makes this approach different from either this approach or this approach. Okay? What's the problem? If we were just doing swapping, and like we did last week, and we moved entire load modules over, when you gave me an address in physical, or rather logical notation, how many tables did I have to look up in to translate that to physical? Trick question 0. There were no tables. There were no table lookups. All we had was a register, maybe if we were doing it right, we had a register that had the offset value in it. We just added the offset value, okay? How many table lookups does this take? Well, how many tables? It's not here, but how many tables does it take to do paging? Someone take a guess.
One.
Exactly correct. 1. Don't you wish you'd wagered 1? Yes. How many table lookups does it take to do this? You guys are cowards.
Still one again.
Still 1 again. Yeah, still 1. What'd you say?
It's still one again.
Oh yeah, you're right. It's still 1. Okay. This doubles the amount of lookups. This doubles the amount of work, and this doubles the amount of work over just doing a single addition. Okay? Because you have to go through and look this up and then do an addition, right? Or look this up, look this up in this table and then do an addition, okay? To get to your location, right? Which is twice as much work per instruction, okay? Per instruction to do either paging or segmentation. How many tables do you have to look up here? It is not 1.
There's 2 on the screen, so let's go 2.
Exactly, right? I love your logic. I love your approach, right? It takes 2 table lookups to do a combination of segmentation and paging. That's a total of 3 times as much work per instruction over just doing direct translation through swapping, okay? So how many instructions per program, per process? Millions, maybe, right? And so now we're doing, each instruction is going to take 3 times as long. All right, that's a fairly hard to swallow hit that we have to take when we do this, okay? So we like what this does for us, right? But it leaves us with a hit. We take a hit to performance on the computer. So how do we fix that? Is there some approach that we can use to, I don't know, not always have to do these lookups, okay? So there's always, I don't know if you guys have taken algorithms. Most of you would have taken 355 by now, right? But I don't know if you took the separate algorithms class. Isn't there an algorithms class that's on offer? It's not called that probably, but anyway, whatever. Whatever algorithms exposure you've had, right? You may have seen that there's a trade-off between calculating and storing, okay? And it's the calculating that we're worried about. This takes 3 times as many calculations to do paging with swapping. So can we trade some of that calculation for some storage? Well, that's the idea of the translation. There's an S in there somewhere. Translation look aside buffer. Okay? So on the CPU, give me a chunk of a register. This, by the way, is even faster than RAM. So why don't we just put everything inside the registers? Because you'd need a $100 million chip. Okay? They're expensive, right? They're super fast, but they're expensive. So can you give me just a little chunk? And with that register, I'll keep a table. And it's called the translation look aside buffer. It keeps a table in it. And it keeps track of as many pairings of SP and F as possible. Right? So when I do a lookup for a certain segment and a certain page, right, it keeps track of what frame number that is in. Okay, and then when I do the next one, SP1, it tells me, oh, that's in frame, whatever. Okay, and I keep a list of all of these. Then the next time I have to look up this address, the first thing I do before I do any translation is I look in this table to see if the SP I'm looking for is already in here. And if it is, then I have stored already on the chip where in physical memory this thing is. So I get to skip all of this calculating. Okay? Of course, I can't keep track. It's not big enough to keep track of all of those numerical pairings, right? So I have to have some scheme for replacing these pairings. And that scheme is based on the principle of locality, which is a fancy way of saying if I have looked up a certain page in a certain frame recently, then it is likely I am going to look up that same page again soon. Okay? So, and why is that? The principle of locality actually says, look, instructions and data are going to be accessed close to each other. Okay? I think did I mention this before? Like the notion being that we don't often call functions, right? And all of our data structures are loops. If we're doing a loop, then those instructions are pretty close to each other. They're going to be called over and over again. Otherwise, if we're just executing sequentially, the last instruction is going to be really close to the next instruction that we need. And the last piece of data is going to be really close to the next piece of data we need, right? It's only rarely that we jump from this instruction down here to do this function over here. And even then, if I do that, then this function will have several different instructions that are really close to each other, okay? So every time I look one up, right, if it's there, I keep track of how recently I have looked that guy up. And if I look one up that's not there, I don't want to replace the ones I'm currently looking up very recently. I don't want to do that. I want to replace the ones I haven't looked up in a while. Okay. So replace the least recently used pairing out of the translation lookup buffer. And you should, according to the principle of locality, minimize the number of times that you have to do all of these calculations. Not eliminate them. There's nothing we can do to eliminate them, but we can carefully use storage on the actual CPU itself to limit the number of times we have to do those expensive address translations. Okay? Any questions? Okay. It seems like I recently graded something for you. Yeah, exercise 5, I recently graded. So look at those. If you have questions about that, let me know. There will be exercise 6 coming out at some point. I have not made it yet, but we need to have another exercise before too long, and I plan on doing that. So be on the lookout for that to come out probably next week. All right, I'm done. So I'll see you guys next week. You guys always get out faster than the morning class because the second time I teach this material, I'm much faster.